Okay, so here's where we were last time. We were talking about Green's theorem, and there's a bunch of say about Green's theorem. So we sort of motivated the theorem, loosely. Again, we're not doing rigorous proofs in this part of the course, really, or at all in this course. But we gave a sort of a plausible development and motivation for it, which I think is exactly what we need. We did some immediate applications, some computational applications, and then we've been showing connections to other things, like how to compute area was what we talked about last time. So then we started talking about this, what I call this relationship to the fundamental theorem of line integrals, which seems surprising, right? This is a very different dimensional context. Green's theorem is about a two-dimensional region with a one-dimensional boundary curve. Fundamental theorem of line integrals is about a one-dimensional domain curve, right, with boundary points, which of course are zero-dimensional. So they seem pretty unrelated. So here's the relationship. You draw this picture like we did last time. By the way, it was pointed out to me just at the start of class that I forgot to explain a notation to y'all. This right here, the partial symbol, is a common notation to represent boundary. I just forgot to mention. I know it's not common for y'all, right? But it's like, you remember that time where I had a phi, right? And then I helpfully it indicated that it was, it's just in my mind. It's instinctive. It means the same thing. And so anyway, my apologies. That was an oops. Okay, so that means boundary. So these two curves start at the same point and end at the same point. And then the idea is that this region in between, its boundary consists of the two curves. Okay, well, yeah, but oriented backwards, right? Because as we go along C2, we're going exactly the opposite of the direction that C2 is going, and thus the minus sign. Okay, all right, so that was all developed last time. And then with this having been sort of, this context having been defined, then here's Green's theorem as it applies to this region. Right? Is there a question? Yeah.
Can you explain how you got one boundary? Is it just
yeah, so this just means, so the boundary of a curve consists of, where does it start and where does it end? Okay. Right? So these two curves, they start at the same point and they end at the same point. That's all that means. Right. Okay, so here's, for this two-dimensional region, here's Green's theorem. Just directly written down, keeping in mind that the boundary of this two-dimensional region is C1 and then C2, but sort of going backwards across C2. So I'm going to say minus C2. So Green's theorem, fine. And then look what happens. This remarkably convenient development happens if Green's operator on some given vector field is 0. Well, that means that the integrand there is 0. That means that this left side of the equation is 0. That means that the right side of the equation is 0. That's how equations work. And wait a second, if we have a vector field where whenever you have any two curves that start and end at the same point, you always get the same value for the line integral, that means path independent. Right? Yeah.
So do you just have to prove that two curves have the same value? Because what if two curves have the same?
Yeah, but this applies to any situation. I mean, I only draw one such picture, right? But the point is, this argument would apply to any such picture that I could draw. So you may be thinking about, what about this other pair of points and this other pair of curves that start and end at the same picture, right? And so same result. Yeah, so we, as these kinds of pictures, and look, there's little issues, there's annoyances that come up of, what if the curves intersect? Like, what if the second curve is, like that? Well, it still works out. There's just issues you have to worry about pluses and minuses, but there's morally the same result. For the purposes of the motivation that we're looking for here, you can just feel free to ignore complications like that. Yeah.
Doesn't this only work because, C1 and C2 are the exact opposites? Like, what if C1 was, a little bit different than C2?
What do you mean?
A
little bit different.
The only reason why we get 0 is because they're the exact opposite curves.
I don't know what you mean by opposite. You mean their orientations?
Yeah.
So this goes back to what we were talking about yesterday. So you can't really compare the orientations of C1 and C2 because they're different curves. They're opposite in the sense of how they're part of the boundary of this region, right? But they're the same in terms of how their boundaries compare, right? They both start at the same point. They both end at the same point. So such comparisons are, I'm going to say, distraction. There's really no meaningful conclusion to draw down that road. The point is, this picture, I can draw any picture I want, right? That picture, here's some true observations. This is an immediate statement of Green's theorem, and we get the conclusion from it. Does that make sense? Yeah. Okay. Okay. So, if Green's operator is 0 for a vector field, and I mean 0 everywhere, right? Then that vector field is path independent, which we already know means it's a gradient. And so what we've done here is we have given a sort of half of an argument about the first lifetime theorem that we wrote down, right? So morally, other than doing calculations, why is it that Green's operator being 0 and the vector field being a gradient, why should those be connected at all? This picture. Right. Okay. By the way, the argument goes the other way. Suppose you have a gradient, right? So instead of this, let's try to go sort of, backwards. Suppose I have a gradient field. Well, it's path independent. We already know that. Path independent means that the difference between any two such line integrals, again with the same picture, right? Any two line integrals, their difference is going to be 0 because they're the same. That means that the right side of the equation is 0. That means that the left side of the equation is 0. And how could that be? How can you have a double integral that no matter what two-dimensional region you pick, the double integral is always 0? What integrand could there possibly be if the value of the integral is always 0? Well, the only possibility is that this integrand is 0. That makes sense? So here's another way to think about these. I'm writing down all the equations and everything, but sort of another way to think about this is let's talk about what is path independence. The idea of path independence is you should always get the same answer when you do two of these kinds of things. Let me speak very sloppily. All right. You should always get the same thing with both of these kinds of deals. Well, that's really exactly the same statement as you should always get 0 when you go all the way around, starting and ending at the same point. You should always get 0. Well, that's a circulation. If you want to always get 0 for your circulation, no surprise, your circulation density had better be 0, and vice versa. So I think it's actually a pretty intuitively satisfying argument. Okay. So one other application of Green's theorem I want to talk about. This one is there's a little bit of foreshadowing in this example that I won't be able to flesh out until a little bit later. So anyway, that's just for callback purposes in a couple of days. So we're going to talk about a new concept. We're going to talk about something called flux. A lot of you might not have heard of flux before, other than as a meaningless sort of science fiction reference in Back to the Future. Right? Have y'all seen that movie, Back to the Future? Okay, some of you have. Some of you haven't. I'm old. So here's what flux is. We're going to start off with the idea of flux through a curve. Flux is easiest to motivate, in my opinion, in the context of vector fields representing fluid flows. Now, again, I've said before that when you're looking at vector fields, when you want to sort of think about and have a physical intuition for what does the calculation that you're doing represent, you have to decide: am I thinking about this vector field as representing a flow of a fluid, or am I thinking about a vector field as representing forces? Right? So when we were talking about line integrals, we were sticking with vector field as forces. And the idea is that forces, as you move along some curve, will the force and the displacement along the curve. That helps you compute work. And we motivated line integrals from the point of view of work, which comes from the point of view of thinking of the vector field as representing forces. Okay, you got to get out of that mindset, right, and into the idea of now we're thinking about a vector field as representing a flow of a fluid, which, by the way, we were already kind of in that mindset, right, when we were talking about Green's theorem. We motivated the idea of Green's theorem from the point of view of circulation. Okay, so field represents a flow of a fluid. So reasonable question. If you've got this vector field representing how a fluid is flowing, so at any given point, right, take some point, the vector field is telling you about, I'm going to say, let's say the velocity of the fluid at that point. Right, it's telling you what direction the fluid is flowing, and longer means it's flowing faster. And if you want to know how much grand total fluid is flowing, let's say, through this curve, right? I mean, that's a different question. The velocity of the fluid is meters per second, right? The total quantity of fluid that's going across that blue line, wow, that depends on how big that blue line is. If you have a bigger line, there's more fluid crossing the line, right? If the fluid is flowing faster, that is going to make more fluid, more total quantity of fluid flowing across that line. So this is not just a matter of what is the field vector. Right? Quantity per unit time is a different thing from what is the velocity of the fluid. All right. And by the way, it also depends on direction. Here's a sort of a silly consideration. I mean, suppose the fluid is flowing, I'm mixing my colors. Suppose the fluid is flowing like this. There's not a whole lot of fluid crossing that line. Whoops. Right? There's a lot of fluid flowing near that line, but not a lot of fluid is crossing over. Does everybody see what's going on there? Yeah. Okay, so what we're really interested in then, if we want to get our hands on, to how much in some sense of quantity of fluid is going across the line, what I really need to know is not what's the magnitude of the vector field, but I need to know what is the component in the, and I guess that's a scalar, so let me do like this. It's what is the component in the direction perpendicular to that piece of curve. So I want to know the component in this normal direction. So normal component of the vector field. So you might say that represents the relevant part of the flow. Right? I don't really care how much the fluid is flowing along the curve. That whether it's moving somewhat to the left or somewhat to the right along the curve, irrelevant. It's only the extent to which the fluid is flowing through, perpendicularly through, that is going to actually cause fluid, quantity of fluid to actually make it across the line. Okay, so the idea is that component times how big is your piece of curve. Purple times dark blue, purple times dark purple, right, is what's going to get our hands on this idea of how much fluid's going over the line. Does that seem kind of plausible? Everybody happy with that? By the way, don't forget our formula for components. Colors. Components are computed with dot products with unit vectors. Let's assume that our little n there is a unit vector. In fact, you'll notice I'm describing it here as our unit normal vector. And so that is computed by f dot n. Okay. All right. So this is our idea of flux of a fluid over a line. Now, just a quick, I'm going to call it a cultural note. I was interpreting here the vector field as representing the velocity of the fluid. That's not always what the vector field represents in a fluid context. There are other situations that you could very reasonably want to consider, such as, well, maybe it's not a constant density fluid like water. Right? The nice thing about water is constant density. Right? It's all the water at the bottom of the Marianas Trench is under tremendous pressure, but it's the same amount of mass per unit volume as at the top of a swimming pool. Pretty much. I don't know. Maybe very slight differences. So water is surprisingly incompressible. Okay. But not all fluids have that feature. Gases, not at all. Right? And hey, maybe we're not talking about a liquid fluid. Maybe we're talking about like a migration pattern of something like birds, right? So maybe there's just a whole lot of birds in this one general vicinity, right? And maybe they're not flying very fast, but just the smallest little slight movements of this mass of birds is going to cause a lot of birds to be crossing that line, right? Whereas if this is very sparse, there's hardly any birds in the flock at all, it doesn't really matter how fast they're flying, right? So sometimes density times velocity is what people talk about for the vector field. But anyway, we're not going to deal with those complications in this class, so let's just ignore that. So the definition of flux is still this formula. Okay. All right. So this F dot n. By the way, notice it looks like we've got a line integral developing here. We've got something times ds. Looks a lot like a line integral. Whatever that's worth. We'll come back to that thought. Okay, so F dot n. I want to talk about F dot n. F dot n. Here's the F. Okay, let me color code differently. There's the F. Here's the n. Unit vector perpendicular to the curve. Right? And so this dot product, F dot n, is what I'm interested in computing. And here's the problem. If I want to add that up over a piece of curve, if this is my, I'm going to say d phi. This is the amount of, small piece of flux going across one little small piece of curve. If I want to add that up over some curve, I'm going to be looking at an integral, F dot n ds. And this, let's see what's going on here. We've got a dot product, right? That's vaguely familiar. We remember doing line integrals where the integrand has a dot product in it. The problem is that in that situation, it wasn't in ds. It was t ds. So if this were f dot t ds, then we're good. We're like, hey, vector line integral, we have lots of existing development and formulas, and we can just parameterize and plug and chug, and we're good, right? This, not really, right? We've never talked about integral f dot n ds. So that's awkward. So here's what we're going to do about that. We're going to make the clever observation that f dot n can be related to something dot t. And the idea is, let's just take this entire picture that I have circled in purple, let's just rotate everything 90 degrees to the left and see what happens. And when you rotate 90 degrees to the left, well, when you take a perpendicular vector and rotate 90 degrees, you get a tangent vector. You get the unit tangent vector on the curve. Yeah. When you rotate a field vector 90 degrees, well, I mean, I'm just going to appeal to your memory of chapter 12. If you want to rotate something 90 degrees, well, this other thing that you're rotating into, the dot product of those two vectors is 0 because they're perpendicular, and it's got the same magnitude, and it's not hard to persuade yourself that when you rotate that, f, this rotation of it, this rotation of it, like that, is just negative q comma p. Yeah? Same magnitude as PQ. Dot product is 0 with PQ. So that's what you get when you rotate. Now, the only question you have to think through is, wait a second, is it negative q comma p, or is it q comma negative p? It could be either one of those by that reasoning I just gave. And to go counterclockwise, minus signs on the left, you can draw some pictures and think it through. I think that's pretty believable. Okay, so punchline is that, let's see here, here we go. Okay. That purple dot product, F dot n, and keep that in mind, that's what we're interested in up here. F dot n is equal to, did I write this down here? Yeah, here it is. F dot n is equal to this F rotated dot t. And all I did is rotate the picture. The vector is in purple, the vector is in yellow. Well, same magnitudes, same angle between them, same dot product. Everybody on board? Okay. All right, man, so how convenient, right? So here's the circumstance we were in, and then I'll go back to the context above in just a moment. But we were unhappy about the fact that we were looking at an integral of f dot n, and how are we going to deal with this? I don't know what to do with, n ds. What is n ds? I'm not familiar with n ds. We know t ds, right? And very conveniently, knowing as we now do that f dot n is the same as f rotated dot t, I can rewrite like so. And now this resulting integral that I have, this is a straight up section 15(2) vector line integral around whatever curve we're looking at. Okay. All right. Very, very clever idea. Now, up here a little bit for context. So let's consider this question. Suppose we're looking at some plane region like this, and we want to talk about the boundary of that plane region. And I want to know what's the total flux through the boundary. So, in the outward orientation, what's the grand total flux of this fluid through that boundary? Now, why would we want to know that? Let's go back to migrations of birds. Let's just say flux of the this bird fluid, right, through that boundary is a way of measuring what's the rate of change of the bird population. That's what the flux is. Flux is quantity of stuff per unit time crossing the line, right? So here, where the where the normal vector is about like that, and the field vector is about like that. This right here represents birds exiting this region. There is a flux of birds out of the region there. Whereas, on the other hand, over here, this part of the curve, there's the normal vector. There's the field vector. This represents a flux of birds into the region. Or you might say, just for the sake of consistency, that in that part of the curve, the sort of the contribution that curve makes to the outward flux, how many birds are leaving the region in that general vicinity? Leaving? They're not leaving, they're entering. So how many birds are leaving? Kind of negative birds are leaving, because the positive birds are entering. Does that make sense? Everybody see what I'm saying? Okay, so what we're interested in then, if you want to know the grand total rate of change of bird population in this region, this flux computes it. Get rid of the. Oh well. Anyway, that's fine. This flux that we motivated on the previous page, that's keeping track for us of the rate of change of birds, bird population in that region. And of course, it doesn't have to be birds; it could be water, surface water flowing across. Maybe we're trying to keep track of, are we gaining surface water in this region of the map, or are we losing surface water, and how much? Right? This does that. Okay. All right, so that's why we'd be interested in computing this. And clever idea discussed on the previous page, that is equal to this. This is a good old-fashioned section 15.2 type line integral, which you'll notice I've rewritten here as dot dx. Right? TDS is the same as dx. The formula on the previous page for what this rotated version of f is that. And we know how to do this. Now, a couple different ways you can go. Now, you might be thinking, what does this have to do with Green's theorem? Weird, the big effect of sort of converting this dot product in the language of normal vectors into this dot product in the language of tangent vectors is that we have translated, to what extent is the vector field going through the curve to what extent is a different vector field going along the curve. So this is, in fact, a circulation. It's not the circulation of, bird flow along the boundary. It's the circulation of this other vector field, perpendicular to the bird flow, right? But nevertheless, it is a circulation around the boundary of this solid region. And so this being a circulation, we can compute that circulation with Green's theorem. This is exactly Green's theorem as applied to that vector field, and that's easy to simplify. You pay attention to the minus signs, and you get a double integral of, it's kind of weird, but dp dx plus dq dy. A little bit surprising. So, calculation involving, how to compute such a flux, total boundary flux. Okay, one detail to worry about in this little calculation. Notice that this formula at a glance looks wrong. I thought it was dq dx minus dp dy. So what's up with the p and the minus q? Where'd that come from? Well, keep in mind that formula is really just on the assumption that your vector field is pq. But when we write down partial of q with respect to x minus partial of p with respect to y, what it really is it's not whatever happens to be named q, it's what is the second component of the vector field. And this p, it's not whatever happens to be named p, it's whatever is the first component of the vector field. Right? So this is a very immediate application of the formula. The second component that I take the x partial of, according to this formula, that second component here is p. Right? And this first component, whose y partial I subtract, is minus q. Everybody on board? Yeah. Okay. All right. So, last quick comment. This formula here, you can think of the way I've presented this here is, because we're in the context of talking about Green's theorem, I presented this as something that you can motivate. If you take the original question and if you kind of turn your head, 90 degrees to the left, then, this flux question becomes a circulation question, and I can apply Green's theorem, and I want to be able to apply Green's theorem because this is the section on Green's theorem. Right. Turns out there is another, arguably more natural way to approach this problem. It turns out that you can view this question as a different sort of accumulation. It's like a sort of a different. It's a different kind of rip-off of this accumulation idea, right? And there's a totally parallel development, and we will talk about that later. So that's, like I say, a little bit of foreshadowing. So keep your eyes out for a different point of view on this, computing boundary flux. Okay. All right. Now we're going to go up to a three-dimensional version of flux. All right. So same story, different details. So you remember the little speech I gave? Sometimes you think of vector fields as representing forces. Sure. If you're computing work with a line integral, then you think of the vector field as representing force. Right? On the other hand, in different contexts, you want to think of the vector field in different ways. Here, we want to think, again, just like we have been, this is just a reminder, we want to think of the vector field as representing the flow of a fluid. The big difference is that now we are looking at the flow of a fluid in space, right? And so instead of talking about, given a vector field in space, instead of asking how much of that fluid is flowing through a line, a natural question to ask in space would be how much of that fluid is flowing through this piece of surface. Right? So if I have some, here's a surface. Right now, nothing will go through my hand tragically. So let me say, here's this piece of surface that I'm going to just represent the boundary of. Right. So if I go, right, if I blow air through this hole, well, how much air is going through this surface here? Right. Perfectly physically plausible question to want to ask. Right. Okay. All right. So same analysis. If you're interested in how much fluid is going through, then I don't really care how fast. Right? I mean, if I take this surface and, how much air is going through, if I turn it to the side, right? There's no fluid going through the surface, right? And here I guess I can just do it with my hand. No air is going through my hand. Right? Okay, so it's not how fast the vector field is or how fast the fluid's going. It's to what extent, again computed with a dot product, to what extent is the fluid flowing perpendicular to the surface that we actually care about. The extent to which the fluid is flowing parallel to the surface, that's just silly. Right? Not going to contribute at all to flux. Okay, so there it is. There's that perpendicular component. And again, I appeal to your intuition. The bigger your surface is, the more total throughput of fluid there's going to be through that surface. Right? The greater the component of the velocity perpendicular to the surface, well, it stands to reason, if you blow harder, then more air goes through. Right? Okay, so perfectly plausible. I guess I have to zoom out a notch. The normal component times the area is going to tell you how much actual, throughput, volume per unit time, quantity of fluid per unit time, right? Air per unit time, birds per unit time flowing through whatever region I have, right? It's going to be that product. Is that plausible? Yeah. So, by the way, quick observation: when you make connections between math and the physical world, again, it can kind of go in two different orders, right? It could be that there's a pre-existing idea that you have, some physical concept that you already understand or have some intuition about, and then you try to write down formulas for it. On the other hand, sometimes you find yourself writing down certain formulas and then say, there's a formula. What does that mean in the physical world? What does that represent, right? So we kind of that happened with us with circulation, right? So circulation, we wrote down the formula first, and then I asked, okay, what does this represent as applies to fluid flows? And we had to kind of come up with this idea of, it's measuring to what extent a fluid is flowing around and it's kind of going around in a circle in a way, and we came up with this idea of circulation. So there's an aspect of that going on here, right? In other words, flux of a fluid is not necessarily an idea that you spend a lot of time thinking about, right? But it fits in very naturally with these math ideas. Okay. All righty. So now again, looking at this picture, there's some sort of assumptions that go into this picture. You'll notice that I deliberately gave us a flat surface. Right? And by the way, it's pretty importantly sort of implicit in this that the surface is flat because, well, I didn't talk about which normal vector, right? I'm sort of assuming that all these normal vectors are the same vector because I just write, in as if it's the same everywhere. What if it isn't? What if the perpendicular to the surface is different directions at different places? In other words, what if your surface is not flat? Okay, well, that's a complication that this formula doesn't address. And likewise, what if your vector field is not constant? I mean, again, it was sort of implicit here that well, just, it's whatever, any value of the vector field, well, that's every value of the vector field, and it's always the same. Well, what if it isn't? What if the vector field is doing something more like this? Well, this formula just isn't going to do it. Right. Okay. So we're going to take our usual approach, what I like to call chop it up, add it up, right? So here's a highly non-flat surface. Imagine a vector field that's non-constant, and so maybe the vector field is, I don't know, something like that. Right? Well, okay, sure, right? It's not flat and it's not constant. Oh my gosh, right? But if you look at some little piece, some tiny little piece there, the vector field, as long as the vector field is continuous, then on a sufficiently small piece of region, the vector field is still not exactly constant, but it's going to be really close to constant. On a really itsy bitsy teensy weensy little piece of surface, it's going to be pretty constant, pretty close to constant. And itsy bitsy teensy weensy pieces of surface tend to be pretty flat too, right? That's why the human race didn't get around to figuring out that the world was round for a long time, right? It looks pretty flat, right? So, okay. So chop it up, add it up. Right? So we know how to compute, on a flat-ish piece with a constant-ish vector field, we know how to compute the amount of flux through that piece. We got a formula on the previous page. Well, if you know how to do it on each little piece, then the grand total over the entire surface is just the sum of all the little pieces of flux that you get through all the little pieces of surface. So again, this is highly consistent with the increasingly great number of kinds of integrals that we've talked about in this class. Now, right, I've kind of lost count. Right? This is going to be a new kind of an integral here, but it's, again, chop it up, add it up. Okay. All right. Now, so we can write down formulas like this, but how do you actually compute them? Right? I mean, it's all pretty abstract discussion until we know how to actually get our hands on it. And how can I turn this into an iterated integral that I can turn the crank on and get, I need to be able to get numbers out, right? So, what do we not like about our domain here? What I don't like about my domain is that it's dimensionally awkward, right? It's a two-dimensional thing in a three-dimensional world. It's not a triple integral. It's not a double integral. What do you do? So, well, we're going to do just like we've done already, previously, right? We've already seen dimensionally awkward surfaces. What you do is if you don't like... I don't think I did a good job. Anyway, if you don't like your surface, if you don't like your domain in general, find a way to view it as the image of something that you do like. In this context, I'm going to view my curved surface as the image of a nice, flat, possibly, hopefully, rectangle in let's say, the UV plane, like that, and then we do a pullback. Right? And so, not only is this similarly motivated to things we've done in the past, this is really, in fact, exactly the same thing that we've done in the past. We've already developed a lot of stuff about this story. Parametrizing surfaces and how does the size of this relate to the size of that? That's all done. Right? Let me just remind you what we know. I already know that I'm going to be looking at xu and xv, that those are both tangent vectors. We know it's going to turn out that the cross product in is going to be an object of interest, right? Somehow. And by the way, just for notational purposes, let me just remind you that from here on out, we're going to be viewing the unit vector pointing in that direction. So the unit normal vector. Very importantly, capital N is not a unit vector necessarily. It's probably not a unit vector. It's the magnitude of N comes from the parameterization. You can see it right here. N comes from the parameterization, right? So the unit vector pointing in that direction, we're going to call little n. We're going to stick with the book's notation on this. So by the way, so be very, very careful from here on out. You cannot just arbitrarily decide to use capital N to represent a unit normal vector anymore. No fair, right? That capital N now means something. And little n, you cannot use a little n in place of capital N to represent XU cross XV. Little n from here on out, you should interpret and use as a unit vector. Okay. And let me recognize this is different from the convention that the book used back in chapter 12. Back in chapter 12, we used little n for whatever, any normal vector. Pick one. It doesn't matter, right? We were very, very flip about that in chapter 12, right? So no more. So be careful about this distinction here. Okay. So, like I say, all of this, existing construction. And then now down on the differential scale, right? Here's our big surface, and here are some big vectors that relate to what's going on the surface at a given point. Now let's go down to what I call the differential scale. So looking at an itty-bitty piece of surface, and we've already talked about, so this is a, not exactly a parallelogram, but it's going to be it's pretty close. It's well approximated by a parallelogram. Let me just draw a parallelogram. And we went through detailed calculations and found that vector is XU du, right? That vector is XV dV, and ds, that amount of area there, magnitude of capital N times du dV. So all of this is done back in chapter 14, I think it was, when we're doing surface area. Yeah, it's 14.9. Everybody have memories of that? Now would be a good time to go back and brush up on all that 14.9 stuff with the surface area and the, where did the capital N come from? Why is ds equal to, magnitude of capital N du dv? All this business. It's a detailed discussion in the notes, old video lectures, etc. Make sure you're good with that. Okay. All right. With all of this set up, I'm going to introduce now one other I think convenient tool to make use of in this context. It's a new object on this differential scale picture. It's called the ds vector. It's this vector here that I was hiding. ds. And it's defined by, take your pick, either one of these things. It is capital N du dv, or it's little n times ds, and I need to first persuade you that these are in fact the same thing. So let me give you my argument for why these are, why are these the same thing here? Well, because both of these things can pretty easily be seen to be little n times the magnitude of capital N du dv. And so here we go. Notice here, let me highlight. Little n times the magnitude of capital N. Well, little n points in the same direction as capital N. So this vector I have circled in blue, it's pointing in the same direction as capital N. It has the same magnitude as capital N. If it looks like a duck and quacks like a duck, right? Same direction, same magnitude as capital N. It is capital N, right? And so this thing I've written above there, it's clearly the same as capital N du dv because of that observation there. On the other hand, this we already know is ds. Right? Capital N du dv is ds. And so little n ds also. So I think that's a neat point of view. It makes it clear why the important punchline here is why these are equal. Okay. All right, now let me get that out of the way. So this ds vector, think of it in either of these ways. They're both really convenient and for different purposes. Right? The second one here is convenient for this next observation. This ds vector its magnitude is equal to the size of the piece of area. Why is that? Well, because the magnitude, here's the magnitude, right? Little n is a unit vector. That's the magnitude. It is ds. So the magnitude is the size of the piece. What is the direction that this ds vector points in? Well, you can see it right here. The direction it points in. What's the orientation of your piece? Keep in mind that normal vector is going to point perpendicular to your piece of surface, right? That perpendicular unit vector, little n, tells you how that piece of surface is oriented, whether we're talking about something like that, or something like this, or something like that, or what have you. Okay. All right. So the way I like to say this is that this ds vector tells you everything you might want to know about the piece of surface. What might you want to know about the piece of surface altogether? How big is it and how is it facing? Which direction is it pointing? That's everything you could possibly want. If you're interested in flux, how much fluid is flowing through a piece of surface? How much area, right? How big? And how is it oriented? And ds, by way of its magnitude and direction, this ds vector tells you all of that with one single, object. So anyway, very convenient tool. If I remember correctly, the book does not use this ds vector notation, but it's pretty standard, and so you're very welcome to use it in Math 212, and I encourage you to use it in Math 212. All right, now let's put everything together then. Let's keep in mind what we're doing here. We're trying to do chop it up, add it up on this surface, right? The idea is on any little piece of surface, I know what the flux is through that little piece of surface. F dot n times area. That's how you compute flux. F dot n times area. Okay, so on each little piece, we want to do F dot n times area. Yeah.
So is the flux equal to ds or
no? No, so ds is just one of the players in that. So we're going to get to that momentarily. We're a couple steps away from it. I'll totally have an answer for you, but we're all not quite there. So we're going to be adding up, right? Chop it up, add it up. We're going to be adding up a bunch of pieces of F dot n times area. And we have all of this context already developed. And so here's how it plays out. We're adding up over the surface a bunch of little pieces of flux that are all F dot n times area. And, don't forget, we already have a notation for the area of our little piece. The area is ds. Right, so F dot n ds. Okay, so this is our formula for flux. Total flux, that formula right there. This is the formula the book uses to represent surface flux of a vector field. Now, I like to write this a little bit differently. This is my personal preference. Everybody's different, right? But so I make the observation that, well, look, this in ds, I'm getting too sloppy with my colors. Hang on a second. In ds, you can write as the ds vector. So this in ds, I'm going to rewrite as the ds vector. Like I say, this is a standard move. Right? And it gives you then, instead of representing flux with that expression, surface integral F dot n ds, you can just write surface integral F dot ds vector. It's a little bit less pencil lead, right? A little bit more compact, and has another nice feature I'll talk about in a moment. But now don't forget another thing we know about the ds vector. We further know that the ds vector is capital N du dv. So that gives us a different point of view on how to represent total flux. The book talks about this formula as well. It's as they must. But another way to to represent flux. All three of these formulas give you the same thing. Okay, now I want to talk about the pros and cons real quick, and then I have just seconds here, but I think this is good thing to get said here. What's the advantages of that notation, F.NDS? Well, this was the very first one we wrote down. This is the one that we can relate to physically. Right? F.N is the component of the fluid in the relevant direction. ds is the area. This is the most sort of physically relatable. Okay. This one, though, has some nice advantages. It's a little simpler to write down, right? And what I like about this, the fact that it's compact to write down is pretty darn appealing, right? But what I like about this is that it has this feature that this differential that we write down tells you everything that you need to know about the piece of surface, right? That is what you might call the complete differential. The differential is always supposed to represent whatever your little piece of the region is, whether it's the width of an interval or the area of a sliced up piece of area, whatever. ds is telling you about that little piece of surface. It's telling you everything you need to know about that piece of surface. It's telling you what direction is that piece of surface oriented. It's telling you how big, by way of the magnitude of ds, is that little piece of surface. So that ds is the complete differential, and so I consider it to be geometrically natural. Right? And maybe not as physically relatable, but it's more geometrically relatable, I think. And again, it's just my opinion. And then what's the advantage of this? Well, this is computationally this is how you compute. This is how you plug and chug. If you want to compute a flux, we need to do the pullback. We need to write everything from the point of view of the parameterization. And notice in here, I can plug in and write down the vector field in terms of the parameters. Capital N comes from the parameters. du, dv are differentials of the parameters. Everything that's happening in this formula is in the UV plane. That's a double integral that you can actually just directly plug and chug compute. So that, of course, also appealing. Okay, talk about the rest of it later. See y'all later. Have a good weekend.